There's three of us from the mechanical engineering department, and we're each going to give you a 30-second or 30-minute little talk about our favorite lecture and, how we integrate mechanical engineering into our daily lives and why it's important to you as a future engineering student. So we'll just give it one more second for people to join, and then we'll get started. If you have questions during a talk, go ahead and just use the chat feature, and we'll call on you afterwards. So you could either type in question or type your question explicitly, and we'll make sure we answer those. We want this to be kind of informal, so feel free to speak up too at the end when we have Q&A. So I think what we'll do is, now that we have all the key players here, Dr. Bashara is going to give his lecture about his interests. So go ahead, Dr. Bashara.
Okay. Cool. So hi, everybody. One thing, let's see. So it looks like there's about, 5 or 6 of you here. What I would invite you to do, you don't have to do it, but I'd like you to turn on your webcams if you can, just so I can see your faces to see if what I'm talking about is, hitting home. If you don't want to or you can't, I totally understand. It's awkward and weird. So I'm fine with that. So anyways, my name is not Tony Levine. I don't know if you see that. It says it's Tony Levine, but my name is actually Sam Bashara. I'm an associate professor in the department. I also teach classes in biomedical engineering as well as mechanical engineering. But today I wanted to talk about this kind of like my favorite lecture, and it's this one about algorithms. And I hope you enjoy it. I'm going to be asking you guys some questions. I invite you to please, engage with me if you can, unmute, whatever you guys want, though. I'll kind of leave it up to you. Okay, so let's go ahead and get started. So again, the whole kind of idea behind this is to give you a feel for what you can expect in mechanical engineering in terms of lectures and what they're going to look like and how they're going to feel, etc. And so thank you, Adrian, Cole, Ross, and for turning on your webcams. I do appreciate it. The reason I ask you to turn on your webcams, by the way, is that a lot of the techniques that I've tried to use when I teach are active learning techniques. I want to gauge, I want to be able to see your faces. If you're going like this, then maybe I'm not explaining it very well, right? And if you're nodding, then I know I'm doing something right. So anyways, thank you. So here we go. So let's go ahead and do this. Okay. Can you guys see that? What is an algorithm? Yes? Okay, cool. All right, so this is a lecture that I typically give in our second course, our second course in the sequence of mechanical engineering. So you start out, you take Mech 103, then you go into Mech 105. So this is like a Mech 105 lecture. The idea behind it is that we talk about these things called algorithms all of the time. And it's important to start to learn to think algorithmically. And so the idea is, so let's talk about what is an algorithm. And it's something that you're actually very intimately familiar with. You maybe have never explicitly called it an algorithm, but you use algorithms all of the time. So an algorithm is just a set of instructions for solving a problem step by step. And that's it. So for example, you used an algorithm this morning. If you maybe, well, the thing is we never leave our houses anymore. We used to leave our houses. This used to be a thing that we used to do. And in order to determine what you're going to wear that day, right? That's a problem. So the problem is that you need to put on some clothes, and what you're going to wear that day might, depend on what the weather's like. What are you doing? Are you going to a job interview? So the problem is what are we going to wear? And then the algorithm will, might be check my phone to see what the weather is, look at my calendar to see what events I have planned, then make a determination based off of those. So in reality, we use algorithms all of the time in our daily lives without even realizing it. And one of the things that you need to learn as an engineer is how to think algorithmically, think in this set of instructions for solving a problem. Like, how do you create these instructions? How do you do it most efficiently? So to illustrate this, I like to think about a phone book. And so when it comes to thinking algorithmically, not all algorithms are created equally. Some are better than others, and we measure those based off of how computationally efficient they are. And I'm going to illustrate that with a little demo here. So I think you can still see me, and you can still see my handwriting. Is that correct? Okay. So here we go. So just curious, have you guys ever used a phone book? Yeah, you have? Really? Okay, so you're like old at heart. What's that, Adrian?
Used to sit on it when I was little.
Okay, yeah, sit on it when you're little, right. So phone books used to be these things that were kind of critical for our daily life. If we wanted to, call up, rent some equipment or something like that, you have to go in the phone book and find the equipment rental company. Everyone uses the internet nowadays, but this is still a useful demo to start thinking about algorithms and how they work in our daily life. So the reality is this is not a phone book. This is a McMaster catalog. McMaster is a supplier of a bunch of engineering stuff. It's actually becoming very difficult to find phone books anymore. So I might have to update this demo in the future. But again, this still illustrates the purposes for our purposes. So anyways, if you don't know, if you've never used a phone book, I don't blame you. But the way that they work, though, is that they're sorted alphabetically by last name. And so you can pretend this is a phone book, and they're usually about this thick, right? Because it contains everybody's phone number in the area. And they're organized alphabetically by last name. So if your name is Adrian Deputat, I don't know if I'm saying that right, I want to go to the D's, right? If your name is Ross Hodson, right, we go to the H's. So organized by last name alphabetically. So here we go. So let's come up with a problem. And so we'll say that the problem that we want to solve is we want to find my friend Mike Smith in the phone book. So we're going to approach this problem like we've never used a phone book before. We don't really have any good ideas for how to approach this. And so here we go. We're just going to pretend like we're dumb, and we're going to start at the beginning. And this is the first way I'm going to try to solve this problem. I open up my book. I flip it up to the first page, right? So here we go. And I look on this page. Mike Smith wasn't on this page. I flipped the page. Well, Mike Smith wasn't on this page, so I flipped the page. Mike Smith wasn't on this page. Not on this page, right? And I can go page. I'm going single page by single page. So my question to you, is it correct? Will this algorithm work? Sure, it'll work. It's just really slow. So even though that algorithm will work, if I go page by page, one page by one page, if there's, I don't know how many pages there are in this, there's 4,000 pages. It might take me 4,000 page turns in order to get to the right page with his name on it. So let's go ahead and draw a chart to describe the different ways that we're going to look at solving this problem. And the chart is going to look like this. So if we have some sort of labels here, we'll say that this is our time to solve on the y-axis. And then we'll say that this is the size of the problem. And so we're just going to think about this kind of generically. So what I mean by the size of the problem is, let's say that, for example, Mike Smith is on the 1,000th page. Well, based off of that first algorithm that I described, it would take 1,000 page turns to find my friend Mike Smith. So if I drew this on this axis, it's going to look like this. And we can just label this with n, where n describes if it's on the nth page, we have to turn n number of pages to get there. Okay, so clearly this is not going to be very fast. So let's speed it up, right? So you're a good student. You come to my class. I like speed. I like efficiency. So you think, oh, I got an idea. And so here's your idea. So instead of doing page by page, let's skip a page. And so now, instead of going this first page, we're going to do one page. So now I'm skipping a page, right? And you can see that. So skip a page. Skip a page, right? And so I can go to this, skip a page. Okay. Does that, so the first question I'll ask you is, does that algorithm speed up this process? Sure, 2 times faster, right? It's 2 times faster. But we would say that this algorithm has a bug. I don't know, does anyone want to offer up what the bug is?
Skip the wrong page with his name.
Boom. It might work. And this is what students tell me. Dr. Bashar, when I ran it on my data set, it worked. It was fast, but it didn't always work. So it has a bug, right? And so this one, the second technique that we talked about, would have a slope that's half, right? It would be 2 times faster. So n over 2. The problem is that it has a bug. So we should say star has a bug. And in this case, it has a pretty significant bug. So if Mike Smith is not on an even page, for example, we're just going to miss him entirely, right? We're not even going to get there. Okay, so we talked about going page by page, slow, but it works. But it's not the right way to do it. We know we can do it faster. All right, well then we know we can do it faster, so we tried to skip every other page method. Clearly, that does not work either. So now we're kind of playing dumb through all this, right? This is not the way that humans look things up in the phone book. How do humans look things up in the phone book? I guess what I'm asking you is, if I handed you this phone book and I told you it was alphabetically labeled, right? And so this is how big the problem is. What would you do? I told you trying to find my friend Mike Smith.
Open it up and flip to wherever the S's are.
Yeah, flip to wherever the S's are. Good. Now, what you actually stated there, Jack, there's a lot of subtlety and nuance kind of contained in that statement. And whenever we're talking about algorithms, we want to be specific. But I'm going to go ahead and try to like interpret what you said, Jack, and I'm going to like maybe make it my own algorithm. Okay, so this is what I'm going to do, because this is what humans do, and I think this is what Jack is suggesting. Here's my problem: 4,000 pages of problem, right? What am I going to do? I'm going to flip it open halfway. So I flip it open halfway. Okay, I'm halfway opened into my book. So now I look at what the last names are on this page. Let's say that I got to the L's, M's, whatever you want. I know Mike Smith is in this half of the book, right? He has to be. I don't need to worry about this half of the book now. So what do? I go ahead and I get rid of this half of the book, and I knew this was going to happen. These pages are so strong. Oh. Come on, baby. Okay, there we go. Boom. Now my problem is half the size. What do I do next? I flip open halfway to this side, right? Flip open halfway here. Okay, now I look. Now let's say that Mike Smith, I don't know, maybe we overshot it this time. Now I know Mike Smith is in this half of the phone book, right? So I got to the X's, I don't know. So I'm in the X's. So I know Mike Smith has to be in this side of the phone book. So what do? I get rid of this part of the problem. I don't need this part of the problem anymore, right? Look at how small my problem is now. It's significantly less. Keep in mind, we've only done 2 operations, right? We flipped it open halfway, then we flipped it open half again. Okay, that's 2. Let's do another one, right? And I think you guys might see where this is going. So here's 3, 4. So, oh, come on. 4. Man, these McMaster catalogs are really high quality. 5, 6. You guys see what I'm getting at here? After 6 operations, look how small my problem is. 7. And I'm trying to be honest. I'm trying to flip it about in half every time. And if you really wanted to nerd out about the math, we could calculate the maximum number of iterations it would take depending on the pages, but I'm not worried about that right now. I think that was 7. Was that 7? So 8, 9 max. 9 maximum page turns in order to get to the solution. And if we look at this one on our chart here, and I'm covered in like paper particles now. But if we look at this curve is going to look like this. And it's actually going to be a log base 2. So this one's going to be solved very, very quickly. And here's the beauty of this last method. Let's go ahead and kind of tear this. So this is what humans would do, right? We'd flip it open halfway. The beauty is we cut our problem in half right away. The very first operation cuts our problem in half. We saw there was a maximum of 8 page turns to get to Mike Smith. That's a max. So, and this is the beauty of that technique, is let's consider, so it's originally, I think it was 4,000 pages, but let's just say, so originally it's 1,000 pages, just for the sake of argument here. So we'll say that phone book is 1,000 pages. Let's say that the next year, Fort Collins is growing, we're growing really fast. So let's say that the phone book doubles. So next year, it's 2,000 pages, for example. So we've doubled our phone book. Let's investigate how this doubling of the size of the problem affects each one of those different algorithms, right? So we have our N algorithm. Let's just say, again, for the sake of argument, that Mike Smith is on the 1,000th page, worst case scenario, right? So the worst case scenario for this algorithm N here If it was on the 1,000th pages, it's going to take 1,000 operations, right? So 1,000 operations to find him. And if it's doubled and he's on the last page again, it's going to take 2,000 operations. So doubles how much time it takes to solve this problem. And then if we look at the next one, well, this one, again, ignoring the bug, we'll say he's on the last page. You know, so the first time around, this took 500 operations, right? Now the next time around, it takes 1,000. So it's still faster, significantly faster, 2 times faster, but it's not, you know, it's still kind of a big problem. All right, are any of you guys math nerds? How many more operations does this one take?
1.
1. Takes 1 more. Worst case scenario. That's the beauty of this technique. So, and this is the way that we want you to start thinking as engineers. You don't think about just what's right or what works or doesn't have a bug. You think about the most efficient way to complete things. And then the way that you can start to do that is to starting to think like a computer. So starting to think algorithmically is one of the goals in Mech 105 that I try to do. I try to get you guys to think algorithmically, think like a computer, think in terms of these steps. And one of the techniques that we can do that is that we can pretend we're a computer. And when we pretend we're a computer, we have to pretend that we're really dumb. Computers we always think of as very smart. We have smartphones and smart computers and smart systems. There is no intelligence to a computer. Computers are really, really dumb. And you have to think of them as really dumb in order to get them to do what we want. So whenever we write computer code or anything like that, it helps to think of the computer as just like the dumbest possible, you know, it's so dumb that you have to describe every single little thing. So the way I like to describe it to my students is that imagine you wanted to tell a computer to go get you a glass of water. You can't say that. It doesn't know what to do. You'd have to say, all right, computer, stand up, walk to the kitchen, open up that cabinet, take out a glass, walk to the faucet with the glass, put the glass underneath the faucet, open the faucet. Like that's what I mean, right? You can't tell a computer, go get a glass of water. You have to break it down to every single step. And if you miss one little thing, so for example, in that example, let's say I said, get up, walk to the kitchen, open the cupboard, grab the glass, walk to the faucet, but I forget to tell it to keep holding onto the glass, it'll just drop it on its way to the faucet, right? Computers are dumb. So let's go ahead, and this is the last little bit to this lecture. Let's break down that algorithm that we like, right? We like this guy here. This one's the best one. Let's break it down into code so that a computer can understand it. And that's the key. And when we teach you programming as an engineer, we don't really care about the programming part. We don't care about that. That's fine. That's for computer scientists to fuss about. We care about the way that you create the program. So for example, if you come to CSU, you're going to learn Matlab. If you go to wherever, you might learn Python. You know, the language is not what's important. What's important is the way that it gets you to think. So so if we kind of write this out in so let's look at something called pseudocode. Again, you know, most of your professors aren't really going to care what from computer language you learn. That does not matter. What matters is that you learn how to get your thoughts down into pseudocode or flowcharts or things like that. So if we think about this phone book and we wanted to write this out in distinct steps to solve this problem, it's going to look something like this. Remember, computers are dumb. So the first step is going to have to be pick up the phone book, or something like that, right? So pick it up, open it, whatever, or sorry, pick it up, get phone book, whatever you want. But you gotta have to tell it explicitly, go and get the phone book. Now, if we're describing it to a dumb computer, the next step might be something like open to the middle. So computers are actually very good at this. We can say open it to the middle. Computers are very good at looking at, you know, if there's 1,200 pages, it's very good at figuring out what half of that number is. So we're gonna say open to the middle. Step 3 would then be something like, you know, look at the last names. So where are you in the phone book, right? So look at the last names to determine where you are. What should my next step be? What do you guys think? What would you do next? What would you tell a computer to do?
Delete the portion that doesn't have the name that you're looking for.
Good. but you're not thinking. So that's good, Adrian. That's good. That's kind of what I wanted you to say, by the way. I know what students are going to say, but you're wrong. Why do I say you're wrong? You're right. So I baited you. I wanted you to say that, but that's not what you should do. Does anyone know what you should do?
You should evaluate the first initial.
What if, I guess, so yeah, that's all coming later. You guys are on like the later step. The first thing you got to do, you remember your computer's stupid. You got to tell, maybe you got lucky. What if Mike Smith was on that page? So whenever you're designing your algorithms, again, you have to remember computers are stupid. So let's look at the last names. Step 4 needs to be, if we're writing this correctly, if, Smith is among names, then step 5 would be call Mike. Does that make sense? You guys, I knew you were going to say what you said, by the way. I'm not, I don't mean to pick on you. Because again, this is what we're trying to teach you, right? This is what we teach you in engineering, is how to think this way. Think like a computer, think stupid. You guys are too smart. You were coming at it too smart. You're too smart, right? You got to be dumb, think dumb. So the first thing you got to do is check, because maybe you got lucky. You open the book halfway. Oh, there he is, done, right? You got to tell the computer to stop. Good. If Smith is among names, call Mike, you're done. Okay, well now what happens if he's not among names is basically what you guys said. So 6 should be something like, else if Smith is earlier, right? Then we could do things like, then we should open to the middle of the left half. Something like that. And then if you wanted to say, and then we actually need something here where we say go to line 3, right? So we go to the middle of the left half, and then we look at the last names, if Smith is among names, right? And then we could create a whole another 9, 10, 11 that mirrors 7, 8, 9, except it's else if Smith is later, right? You guys see where this is going, I think, I hope. Opened to the middle of the right half. And then go to line 3. Now, let's see, I got 3 minutes. Okay, so I'm going to tell you guys a story. When I was young, I grew up in Seattle, so I grew up in the Puget Sound, and one of my friends actually lived on the Puget Sound, lucky guy, and he had a dog, and it was a stupid, beautiful golden retriever, just one of those like loyal, will do anything kind of dogs. And when I went over to his house the first time, this guy tells me, hey, Sam, make sure you don't throw rocks in the water. You can't throw a rock in the water because my dog is too dumb and it will try to fetch the rock and it can't find the rock because it's sunk to the bottom. So it'll just swim in a circle, right? So what's the first thing I do? I'm like 12, right? I throw a rock in the water. I have to see this. And so sure enough, the dumb dog goes out there and starts swimming in a circle. We have to get into the boat and like row out there and drag the dog out of the water. Okay, why did I tell you that stupid story? Computers are like that dumb dog. What needs to be? So I'm going to add one more condition here. I'm going to say else. What's line 13? You got to tell it to give up. You have to tell your computer, if you don't find Mike and you keep running and you ran out of pages, you got to stop. Now, some of you may have seen this type of error, right? So you'll see the blue screen of death. There's like a Windows thing that used to come out about this. Or those sorts of kind of problems, these infinite loop problems. These occur in computers. These are errors in computer programs that pop up from time to time. And it's basically when a computer programmer never considered the possibility that Mike Smith is not even in the phone book, right? What happens if Mike Smith isn't even in there? Well, we have to consider that, right? And that's what it means to think algorithmically. And then I could go into, I'm out of time, but then we could go into like, what are all these decision statements? That's typically the next thing I'll do, just as a real quick preview. We call these decisions, and those are how we get our program to do different things, and et cetera, et cetera. So anyways, that gives you a little taste of what it's like in Mech 105. I got like 1 minute. Are there any questions I can answer for any of you all?
Yeah, I have a question.
Sure.
So you mentioned that we'd be learning Matlab. Currently in my AP Computer Science Principles class, we've been focusing on Python this whole year. How's the transition from Python to Matlab? Is there going to be a lot of relearning, or general concepts are going to stay the same? Yeah,
that's a good question. So in Python, I would argue is actually better to learn first than Matlab. So Matlab is weakly typed and it's scripted. So there's a bunch of nerd terms there, but okay, so this is what I'll say. Matlab is kind of like Python with training wheels, and the training wheels though are very useful, especially for engineers. So Python's a little bit more of like a pure programming language where you have to define your types. Matlab is going to do a lot of things for you, so it's actually very easy. The transition from Python to Matlab is pretty easy. Transitioning from Matlab to Python is much more difficult. And that just has to do with the way the computing environment is set up. So easier. Matlab basically lets you get away with a lot of things that Python would not let you get away with. So by learning Python first, you actually have good programming techniques already built into the way that you program. So I would say it's a good thing that you've learned Python first.
Wonderful, thank you.
Anything else? I am running a little over. Okay, cool. Well, thanks for turning on your webcams and stuff. I know it's awkward. I do appreciate it. So hopefully that gives you a little taste. Again, my name's Samuel Bechara, Bechara. You can look me up on the Colorado State website if you have any questions or anything that I can help with. You can feel free to email me or something like that. Cool. Thank you.
Thanks, Dr. Bechara. I think you have to log off, but yeah, if you have any questions or follow-up, feel free to email any of us. Dr. Roberts, would you like to go next?
Sure, it sounds good.
Okay.
Hi, I'm Dr. Roberts. I'm an assistant professor of practice in the Mechanical Engineering Department, and I'm going to share my screen so I can show you my favorite lecture. Let's see. All right, hopefully you see my screen now. So I'm not sure that this necessarily qualifies as my favorite lecture of all time, but I want to present something that I think is a very important topic, and it's also easy to digest in these 20 minutes. So today I'm going to introduce you to the concept of tolerancing your dimensions. So I don't know if any of you have done computer aided design, like perhaps learned SolidWorks yet, done some drawings. I'm seeing a few head nods. So hopefully you're familiar with this topic of dimensioning your designs. And tolerancing your dimensions is something that is critical to good design, but it's often overlooked by the novice engineer. So I want to, today I'm going to shorten and combine a few of my lessons that I give in a sophomore level course called Mech 201 Engineering Design 1. So assemblies of piece parts is what makes up most engineered products. And a critical component of producing a quality product is the reliability. Reliability stems from accounting for these manufacturing variabilities, and which minimizes the likelihood of these piece parts not properly fitting together. So in other words, to have a reliable product, you need to have, reduce the consequences of inevitable manufacturing variability. So without considering manufacturing variability in your design, parts might not fit and or work properly, which can lead to product failures and worse, injury or death. And we've seen that a number of times with engineered products causing injury or death. So you need to make sure you have a reliable product. And tolerances are used to control the manufacturing variability to a level that is still cost effective, yet produces an acceptable level of reliability for the assembly and the functionality of the product. So to define tolerance, it's the total amount a dimension may vary from the ideal value, the hope for our dimension value. In other words, tolerance is the difference between the maximum and the minimum acceptable limits of a dimension. So take, for example, this the manufacture of a piston ring. And piston rings are used in internal combustion engines to seal the combustion chamber, among other functions listed here. And this table shows the internal diameter, measured internal diameter, taken from 25 piston rings that were produced using the same method of production. And for each ring, 5 measurements were taken around the ring for the internal diameter. And what we can see is that these diametric values differ in a single ring and also among all of the rings produced. And if we were to plot that table as a histogram, we get this nominal value of 74, but we have a deviation from that nominal, perhaps the ideal diameter for the piston ring, as much as 0.035 deviation way down here. Although you can tell from this histogram, it's unlikely that you would get that diameter size. And the problem is not that these piston rings are imperfect. They're not perfect circles. That's not really the problem. The question is, will they still fit and will they still function as they should? And as long as this range of values that we see is within the tolerance limits set by the engineer, that means there should be no issues with the fit or function of these rings. So this variability when we're manufacturing stuff, it's just a fact of life. There's no way to get around it. In fact, it's impossible to produce anything exactly the same way every time. So any ideas where this kind of variability in manufacturing comes from? Can you think of reasons why we just can't control the manufacturing so precisely to be perfectly manufacturing every part the same way every time?
Just natural vibration, wear and tear of machines, stuff like that.
Yeah, those are great answers. Yeah, there's a whole list of things that can go wrong, so to speak, while you're manufacturing, and these are called manufacturing errors. And there's 2 main categories of them. The first is systematic or bias errors, and they have to do with faulty manufacturing system, the manufacturing system itself. For example, that can be the instrumental errors. That's part of the bias, which includes the wear of tools, like you mentioned, friction, aging of the machine, consistent misuse of the machine, if it's just not operated properly. And these systematic errors also include environmental conditions, such as, where you're operating a machine, what is the pressure, the temperature, the humidity that can affect the precision of the machine. And then the second group of these manufacturing errors are called random or precision errors. And precision errors are the noise in the system. As you're saying, vibrations, that can be certainly a noise fluctuation in the system. And it could also depend on who the operator is, their skill level. That can change from manufacturing one piece to the next piece, the skill level of the operator, and also those environmental fluctuations, which means as you're going through the process of manufacturing one piece part, the environment might be changing quite rapidly, potentially, and the local, especially local environment, temperature changes and things like that. So the main takeaway I want you to have from this is there's just no way to perfectly produce anything ever. Instead, we have to rely on proper tolerancing to guarantee the fit and function of our designs. And tolerancing dimensions specifies the amount of that acceptable variation in the dimension. And the amount that each dimension is allowed to vary depends on the part function, what's that dimension supposed to achieve, the assembly of the piece parts, and the manufacturing process that you're going to use to make that part. So for example, if you're designing a jet engine part, you're going to want to have tighter, in other words, smaller tolerances, acceptable ranges, than if you were designing a bookshelf. And those tighter tolerances that when you have tighter tolerances, that automatically equates to more costly manufacturing. So there is a relationship there. And so tolerancing is a balancing act between making sure you keep your costs to a minimum while still ensuring that your product is going to function as it should. In other words, you're making a reliable product. So I just want to show you how you can specify tolerances on a drawing. And there's different ways to do it, depending on your goal. There's unilateral tolerances, which means that you specify an acceptable deviation in only one direction. So in this example, our nominal value for this dimension is 12 millimeters, but we're saying that we'll allow the dimension to be as high as 12.1 millimeters, but it cannot go below 12 millimeters. That's where the 0 comes in on the tolerance. There's also bilateral tolerances, meaning that there's an acceptable deviation in both directions. In this case, 22 is our nominal value. And we say you can produce this feature on this part with this dimension up to 22.1 millimeters and as low as 21.8 millimeters. There's equilateral tolerances, and that means it's a bilateral tolerance that has the same deviation on both directions. And that's indicated by this plus minus symbol, meaning plus or minus the 0.2 deviation from the 22 nominal value. And finally, tolerances can be indicated by specifying the limits of size for that dimension instead of a nominal value. And when you specify the limits of the dimension like this, you're basically saying there's not really a nominal value to target. As long as you're within the size range, you're good. So before this concept of tolerance was established, every part had to be custom made, custom fit to its mating part. If only one part of an assembly failed, the best case scenario would you'd have to either make a custom fit replacement part, very costly and time consuming. And the worst case scenario is you would have to scrap the whole assembly and buy a new one. So imagine a world, because this used to exist, where something as simple as a threaded bolt you would have to purchase that bolt with its mating nut, with its matching nut, and there were no other nuts guaranteed to fit that bolt. So early in the Industrial Revolution, all parts were handmade and assembled. Every single part of an assembly was painstakingly adjusted to fit perfectly into its mating part. And typically, one business would be responsible for making every part in that assembly, because there was no standardization and everything had to be custom made. But in today's modern world, we're able to have different companies making different parts. And then thanks to tolerancing, we can bring all of those parts together and make an assembly that doesn't need any adjustments at all. So the modern day concept of interchangeable parts started to take off around the beginning of the 19th century. And any ideas of what spurred that innovation to be able to have interchangeable parts you could easily swap out
The Civil War, right?
Say it again.
I think it was the Civil War. One of the wars.
Yep, it was war. It was war because, as you can imagine, weapons and particularly firearms, they were in need of having these easily and fast to swap out parts. And there's so many piece parts in a firearm, and every advantage counts in a war. So when you can have something small gets damaged in your firearm, you can change it out quickly. That meant you had the advantage in the war. So that's really what spurred this innovation of tolerancing and part standardization. So several factors go into tolerance selection. And the first we'll focus on is cost. When choosing the proper tolerances for your part, you must carefully consider every dimension of the part, keeping two main factors in mind: the design intent and the manufacturing cost. So we'll start with discussing what happens to the cost of a part when a certain tolerance is specified. The cost of a part rapidly increases as tolerances are tightened. For example, decreasing a tolerance from plus or minus 0.010 to plus or minus 0.005, that seemingly small change can more than double the cost to create that part feature, just that dimension alone. So the increased cost stems from more time and different manufacturing operations needed to achieve that tighter tolerance. It's harder to achieve tighter tolerances. Plus, the reject rate for the part might increase quite a bit because meeting such a tight tolerance is less likely to occur. And the required tolerance for a manufacturing process must be carefully considered and matched to achieve the desired product quality at minimum cost. So it's always this balancing act. You can't simply just demand a high machining precision, tight tolerance for every feature of your part and say, done for the day. Because when you do that, not only might it be difficult to actually achieve those tolerances through machining, but there could also be material limitations, and it's certainly not cost effective, or it's very time prohibitive to have to machine those tight tolerances. So take, for example, this very simple, seemingly simple cylindrical steel shaft. So if we wanted to manufacture this cylindrical steel shaft here, the graph shows the percent cost increase on the vertical axis versus the tolerance specified for the diameter of the shaft. And what you can see is the cost increase is exponential as you try to get tighter and tighter on the allowable size of that shaft diameter. So the question you need to ask yourself is, what is the loosest tolerance this shaft could have while still achieving the required functionality for the shaft, what that shaft is supposed to do in the product? And there's a lot that goes into answering that question. It's not a simple question to answer, but we will touch on it briefly later in this lesson. So it's important first to know that each type of machining process can achieve a specific and limited range of tolerances. And that's what this chart is showing. It's listing the different machining processes and their typical achievable range of tolerances you can hope to achieve by using that machine. Of course, these are just rough estimates, and the tolerance you can achieve on a particular machine is going to depend on what type of machine, the brand, the model, the maintenance, upkeep, the skill of the machinist, etc. So, but you as the designer and engineer should always be aware that the machining process used to make a part, what machining process is being used to make your part feature. So that's part of the design process, is knowing exactly how your parts are being made and being realistic about what can be achieved. So if a particular feature is not critical to the performance and functionality of the part, because not all features of a part are going to be critical to its functionality, then you should specify the tolerance for that feature at something easy to achieve by the machine that's being used. In other words, a nominal value that expected tolerance for that machine. So for example, if you're machining a base plate for a TV stand, the bottom of a TV stand, the tolerance for that is really not important. It's not going to affect how functional your TV stand is. It's still going to stand up even if you have quite a wide range of acceptable dimension for the base. So you figure out what machines can be used to manufacture the base, and you select something in the middle of its tolerance range. All right. So hopefully, if nothing else, this information has made you realize the importance of considering costs associated with your design specifications, those tolerances, and never arbitrarily assign tolerances because these specifications must be carefully considered and whenever possible, reduced to the most easily achievable values. And you're probably going, okay, so how do I know what specifications are appropriate for a particular application? Because at the end of the day, we need our products to function, right? I think we have a little time left, and I'll talk about that briefly with design intent and how your design intent leads to proper tolerancing. So now that we know how much tolerances affects cost, we must be deliberate in specifying our tolerances. Of course, the #1 priority of tolerancing is to guarantee our assemblies fit and function as needed. With any design, we must first identify the functional features of each part. The functional features are the ones that typically those interact with other components, or they come into contact with other parts. And you can consider those the functional features because they have to interact or do something. And often these contact points, they're going to be dynamic, or they're going to move during operation of the product. So they're critical to the performance of the product. These functional features should always be dimensioned and toleranced first, and then you can finish dimensioning and tolerancing the remaining features of your part that are not directly related to the successful functioning of the assembly. So those non-critical features should receive tolerances that are easy to achieve by the manufacturing process used. And for example, just when you know the type of machine you're going to use, choose a nominal tolerance that that machine can easily achieve for the non-critical features of your part. So let's take this example shown here. This is a linkage bar, and it connects two shafts, each of which mate to into the two holes seen in this linkage bar. So could you guess what are the critical features of this linkage bar? What matters most in this design?
The diameters of the thing on either end. Whoops.
Mm-hmm. Yeah, certainly the diameters of the holes that those shafts have to fit into, those are critical, and probably very critical to the functionality of whatever the shafts have to do. And potentially the distance between those two holes is critical to the functionality. So those are our critical features. And then what do you think are non-critical features of this linkage bar?
Probably the outer diameter of the hole.
Yeah, basically that the outer size, the outer dimensions, the shape of this. It's not critical to make sure this has a very specific radius here, for example. Probably not going to affect the functionality of this part. So as you can see, the first things we've dimensioned are those critical features, and they have relatively tight tolerances, that plus or minus 0.005. And then after we've finished making sure those tolerances are properly specified, we can go on to dimension those non-critical features with much looser tolerances, 0.05 here. All right. But you might be asking yourself, like, how do you know what tolerances are appropriate for certain functions that you want to get out of your assembly? And so let's look at an example of why it's important to know what functionality you're trying to get out of your part. So currently we have a hole and a shaft that mate. Right now, they're just both dimensioned with their basic diameter, There's no tolerances given. So can you imagine if a machinist received this information and they only had the basic diameter, what potentially negative outcomes could you imagine when you receive these parts back and you try to assemble them?
The shaft is too big or the hole is too small.
Exactly. It could be, let's start with the shaft being much smaller than the hole. And you go to assemble this and there's just a lot of play between the shaft. You can move the shaft all around in the hole. And this might be critical. This might be a problem if the point of that shaft is for some alignment purpose. And so you need that shaft to fit quite snugly into the hole to make sure that whatever you're trying to align aligns properly. Another issue, you could get it back and the shaft's much bigger than the hole. And now you're going to have to forcefully mate these two pieces together. And there's no possibility that that shaft could rotate in the hole after it's installed, which that would be very bad if the point of the shaft is to be able to rotate. We have a lot of machinery that has rotating shafts. You know, usually they're on bearings, but point being, you could easily have that functionality needed for the shaft. No way it's going to happen if you have to force fit them together. So that's where the tolerance comes in. But of course, you need to know what's the purpose of this shaft. And let's say the purpose of this shaft is that first purpose, which is to precisely locate, let's say, a third mating part that would be slid on the opposite end of the shaft. So it's not shown here, but let's say there's another part. So the shaft goes into this hole here, and then a third part is on the opposite side. And that third part is going to need to be properly aligned with some other feature that's on this part with the hole. So the shaft just serves as an alignment tool for these two, the part with the hole and a third part not shown. So knowing this, we can go to a standard. There's a standard that's been produced for fits. And fit is, all that means is the degree of tightness between mating parts. And so people have figured out that if you want this type of locating shaft without having to force fit it together, then you can use these tolerances shown here. And all you would need to do is go to the standard for fit, look up your shaft and hole's nominal value, and it would tell you the tolerances you want for this. This would be a close fit that doesn't leave any room for the shaft to move around in the hole, but it also is not a force fit where you can't at least, rotate the shaft a little bit if needed. And it's a perfect fit for this particular application. So that's all I have time to teach you today, but hopefully you've recognized the value of proper tolerancing. And of course, MEC 201 would go into more detail about how to use these standards of fit. Any questions for me? Great, thank you for listening.
Thanks, Dr. Roberts. It's great. And yeah, this kind of ties into what I teach, which I'll go here in a minute once the screen, if you could stop sharing your screen,
yes,
Bonnie, that'd be awesome. Thank you. All right, so hi everyone. My name is Dr. McGilvray. I am faculty here in mechanical engineering. I used to say I was inbred to CSU, meaning I got my undergraduate, my master's, and my PhD here, but that's not very PC anymore. So I say I'm homegrown, as it were. So I love the mechanical engineering department here at CSU. The stuff we do, the educational quality we give, I think is top notch. It allowed me to stay here. So if that speaks for anything to it, there's my general feel about it. So I teach 3 classes inside the mechanical engineering curriculum. The first being structural finite elements. So that's a 300 level class. It's a core level class that you would have to take. In that class, you learn how to use programs to run finite element analysis. We've all seen finite element analysis before. It's a it's a computer model that we can represent 3D structures and apply loads and boundary conditions, material properties, and those types of things, so we can determine if they're going to fail or not. For example, what Dr. Roberts was just talking about, a lot of times we would check fit, mechanical strength, assemblies, that kind of stuff. I teach another class, machine design, that's Mech 325, again, a core class that you would have to take. And in there, we would look at components of machines. So how do we develop bolts? How do we develop things that are going to be in contact, whether that's sphere on sphere, such as in a bearing, or sphere on flat surfaces? We talk about impact loading, failure analysis, all those type of things. And then finally, I teach a class called Mech/Biome, meaning it's in the School of Mechanical Engineering, or the Department of Mechanical Engineering, as well as in the School of Biomedical Engineering. And that's a 500 level class, 573, and it's structure and function of biomaterials. So what I'm going to do is just spend 30 minutes talking about my background, because I have two taskings. One is to teach, to educate the next generation of engineers. And then the second is I have a research mission as well. So I'm going to kind of tell you how I use my mechanical engineering background and the classes I teach and how it relates to the research I do. Because for me, it's all about translation into the real world. And I think the things that I teach in my class, well, it may be fundamentals and we may talk about a simple cantilever beam. That beam can represent many, many things in the real world. So for example, it could represent a new novel robotic prosthesis for a finger, right? So I'm just going to talk about those and kind of give you a glean of how I tie all of these things together, such that when you graduate from CSU in the Mechanical Engineering Department, you can go out there and use this information basically to do anything you want. I've had friends, colleagues, come from our department and basically do things from package engineering to rocket ships to biomedical to entrepreneurship, all of these things. So I think these classes really prepare you to be a high quality engineer in the field. So with that being said, I'm just going to share my screen and give you a little bit background about myself. Let's start with this one. So hopefully you can see my screen, just showing this PowerPoint here. So what do I do? Well, from a research standpoint, what I'm interested in with respect to mechanical engineering is developing technologies that can improve musculoskeletal health. And when I mean musculoskeletal health, I'm talking about things we do to our body, specifically the bones and the soft tissues in our body, following disease, such as getting older, or genetic diseases, or trauma, such as car accidents or falling off your mountain bike. So how do I look at these? Well, I use comparative animal models, I use computer models, I use benchtop models to represent what I would expect to see in the human condition. And then how do I look at my technologies? Well, I look at it a variety of length scales. So what we can see here is I look at it mechanically. So what we're seeing in these two images, this image right here shows a tendon of the rotator cuff. The rotator cuff is your shoulder, basically. So we're mechanically assessing that tissue to determine its mechanical strength. How does it change during disease? If I put an implant in there, how does it change? Does my implant recapitulate the mechanical strength of that? Here we see a test of a biaxial, meaning I'm taking a piece of tissue and loading it in two directions at once so I can understand its stress strain profile. And then I look at its architecture. Sorry, I'm going to close my door here before my cat goes nuts. Shh, we're in lecture. Shush. The joys of working at home. You got to deal with the animals. So here I look at the architecture. Mechanics is definitely driven by the geometry of the shape, right? We hopefully can understand that a porous structure is going to have different mechanical responses than a solid structure. Hopefully we can appreciate that. And then I look at it histologically. So for me, I go down into the length scale of the cells. What are the cells doing? How is that changing the architecture? How is that architectural change changing the mechanics, so on and so forth? And even we'll get into the genetics and things like that. And it's one thing, I think, maybe 25 years ago, a mechanical engineer was expected to go tinker in an engine, right? Build big diesel engines, be in the power industry, those kind of things. Now, mechanical engineering, we can play in any space you can imagine. We can be in outer space, we can be in the body, we can be in novel new technology. So mechanical engineering really allows us to probe things scientifically at a variety of length scales and then contrast and compare all of those. And then the last thing I kind of look at is I do a lot of finite element analysis. As you can imagine, there's so many things that it's intractable to build in real life and do analysis on. So for example, if we look here, I have this little scaffold. I want to use this to say repair a herniation in one of your discs in your spine. Well, I can't just print 1,000 different kinds of flavors of scaffolds and put them in an animal model or use them in a benchtop. It's just intractable to do that. It takes too long, costs too much money. But I can assess them mechanically at least, and some level on the cellularity inside a computer model. So all the classes I teach allow me to do this in the research space. So let me just talk about a little bit more of what I would do for a typical research cascade. And then I'll talk about the classes I teach and how I use that information to do this. So imagine I want to develop what I'm calling an instructive implant. So I want to develop an implant that actually is instructive, meaning that it actually tells the cells of the body what to do. I want it to grow specific cell types. Well, what I would first do is I would go into a computer model and create, say, a model of the spine. That's what we have here. Here's one of the bones of your spine. Here is the intervertebral disc, the soft tissue, and here's another vertebral body of the spine. Probably everyone's heard about disc herniation, right? It happens to athletes, it happens to young people, it happens to old people. What happens is the soft tissue here weakens and bulges out. That bulge can impinge on the spinal cord and cause issues. So what do? Well, as a mechanical engineer, I could go in there and create an implant to replace that tissue. So here we see my implant. This is kind of the generic shape. I run some simulations and I say, yes, my implant has the mechanical strength I'm looking for. It can integrate, it has good stress strain profiles, the hydrostatic pressure is good inside the implant, all those things mechanically. Then what I can do is I can 3D print that using a variety of technologies we have available at CSU, and then I can assess it on the benchtop. So meaning I can take my device, I can put it in a mechanical loading frame, I can seed it with cells, growth factors, stimulants, mechanically load it and see what happens on the benchtop. Do the cells, are they happy? Does the device fail under fatigue? Those types of things. And if it works, then what I can do is I can go and put it in an animal model. Those animals can go out 6 weeks, 6 years, 6 months. We can look at the tissue using radiographs, ultrasound, see if it's actually integrating. And then when the animal dies or we sacrifice that animal, we can take the tissues and mechanically assess it to see if it actually does what we wanted. And then we bring that back into our computer model and say, hey, did my computer model actually match what I see in the real world? And the cool part about this is from a mechanical engineering standpoint is in the in silico space or in the computer space using finite element, I know that certain cell types, so for example, bone cells versus tendon cells, like a different mechanical environment, right? They're fundamentally different. So if I can take my scaffolds and change the architecture, change the material properties such that I have different regions of mechanical response, I can make different cell types happy. So now I can say, for example, have this core here, hopefully you can see my mouse, that can grow into annulus fibrosis cells, while these flares that hook into bone can actually turn into bone. So now I've instructed the cells using mechanical engineering principles to do what I want inside the body, okay? And we also do a variety of other things, again, all using mechanical engineering principles. This is kind of a neat one. We're using electromagnetic waves, RF technology, basically to tell if bones can heal or not. So typically we use radiographs, but radiographs can take 6 weeks, 6 months, a couple of years to determine if bones are going to heal correctly. Well, we believe just using radio waves and some mechanical loading on the limb, we can tell if a bone is going to heal or not within, say, the first 30 days after surgery. And that's really important because if we can say, hey, you know, in the first 30 days, a bone's not going to heal, well, now the doctor can give you growth factors, steroids, and actually drive that bone into a healing cascade. Again, we help develop new models to look at new novel technologies. And again, we assess those mechanically, architecturally, cellularly. So again, applying mechanical engineering principles to the biology space. Down here, I'm just talking about here, again, we see our scaffolds, 3D printed scaffolds. We're looking at the mechanics using digital image correlation. But here what we're doing with our collaborators is we're actually taking orthobiologic therapies such as stem cell therapies, growth factors, embedding those into our technology and seeing if we can improve wound healing. And the reason we do this is we do this not only for ourselves, but we also help some of the largest medical companies in the world assess their technologies. And again, we assess those using mechanical engineering principles. So just to give you a background is, you know, we can use mechanical engineering principles, some of the things I'm just about to talk about, in a variety of ways to really improve the quality of life of people. So does anyone have any questions about that before we proceed? All righty. Okay, if you have any questions, just speak up. I'm happy to answer them as we go. So what we're going to do is now I'm going to jump into one of my lectures that I give for, this is kind of a lecture I combined in my 325 machine design, as well as my advanced biomaterials class. And you'll see how engineering kind of plays a role here. So let me share my lecture, my screen here, a new screen. Share. Okay. All righty, hopefully you can see my screen. I'm writing on it. So as you can imagine, as a mechanical engineer or any engineer, there is a vitally important relationship between material engineering behavior and engineering mechanics. Specifically, we can't know about one without knowing about the other. So imagine I take a bar and one bar is made out of steel and one's made out of wood. Well, I can understand the mechanics of that bar, say if I load it in compression, but the material itself is going to dominate how that responds, right? We can appreciate that. Steel is stiffer, it's heavier, it has different electrical conductivity than wood and all those things. So we need to think about that. So as a mechanical engineer, there's really 5 flavors of mechanical loading that I would think about. Can anyone conjecture what those would be? I'll start with the first one. Let's just say what I'm discussing, compression. That's one of the things as a mechanical engineer, one of the loading regimes that I can focus on. So if I have my generic block here, one of the things I can do to it as a mechanical engineer is compress it. Does anyone want to guess what the other 4 are? So I have compression, I have...
I don't know what the names for them would be, but maybe like a twisting.
Okay, yep. I'm going to call that torsion. So exactly right. So I can take this gizmo or gargus or material and I can twist it. So we call that torsion. All right, what else we got?
You can bend it.
Bending, yep, that's a good one. So I'm going to say it like this. So I can take this, apply loads like this, and I can bend this into a U shape, bending. Good, what else do we got? What's the opposite of compression? There is
Stretching.
stretching, yep, I call that tension. But yes, I can pull on this. And then lastly, what's the last way we can load this? When we rub 2 things with respect to each other up and down, what is that called?
Friction.
Friction. We generate friction. It's called, does anyone else want to take a guess? You're right. We've heard it as shear. We're shearing parts with respect to each other, right? So if I'm trying to take this, let's draw a little pseudo crack or something here, push it that way and push it that way, and I get shear. Okay, so those are my 5 flavors of bending, right? And they're not discrete, meaning I can have compression, torsion, and bending all combined on the same component, right? It's a 3D world. We have 3D multi-axial loading. But in machine design, as well as any kind of materials class, we have to understand how each of those flavors of loading actually contribute to the overall stress. As mechanical engineers, what do we look at? We look at stresses, we look at strains, we compare those to our boundaries of our material properties, right? Because if we go past, say I take a bar, I apply tensile loading. If I load it enough, what's going to happen? That part's going to yield, it's going to stretch, and then eventually it's going to fail. So us as engineers is understanding that relationship such that things don't fail or they fail when I want them to fail, right? Sacrificial parts. So if we look at these components just real quick, an interesting thing that you may not realize is that if I have a component and I'm loading it in tension, I'm going to draw it this way. I'm going to take my generic piece. This can be anything that you can imagine. I'm going to load it like this. Well, what is the stress? So stress, sigma. Stress is this force, F. And this This is some area. Area A. This is some force. Well, stress in the system is just our force over area, okay? So if I look at the stress being one of our critical components, because again, we can compare that to the ultimate tensile strength of this material, whether it's steel, aluminum, wood, composite, biologic, whatever have you. Well, if I look at the stress distribution, what does it look like? Well, it is uniform, meaning no matter where I probe through the thickness of this part, you can see that it's uniform, okay? So this is axial stress. I'm going to just say sigma axial. Well, what's interesting now, let's just look at another one of our flavors of loading. Let's say bending. Where now this bending, I'm going to say M. Bending is caused by a moment. Bending moment, hopefully you've heard that. So what does its stress look like? Its stress has the formulation of M Y over I, where Y is a distance inside my component, and I has to do with geometry. I equals a function of shape. All that's to say is that my I would change if I had a circle, a triangle, shape of a bone, moment of inertia, that's what it's called. So what's interesting about this, so if I'm bending this, and here is my neutral axis, meaning the middle of the bar in this case, what would we expect to be happening at the top of this component? Does anyone want to guess? We're bending it up, creating a smiley face. Imagine this beam is made out of a bunch of fibers or noodles or whatever. What would the fibers at the top be doing? What kind of load would they be under now? Think about the fibers, you're bending something up. What's happening to those fibers? Are they elongating or are they stretching or compressing? They're compressing, right? So at the top of this beam, what we actually get is compression. And it's a linear compression that goes down to 0 at the neutral axis. So that means at the neutral axis, there is no stress in bending, okay? That's an interesting finding, meaning if I know that and I want to drill a hole in this part under bending, where would I drill that hole? Well, I'd probably drill it in the middle of the beam because there's no stress there. No stress, no failure, right? So then what's happening at the bottom of the beam? If the top fibers are being compressed, what are the bottom fibers doing?
Stretching.
Yeah, stretching, right? So now I have the opposite on the bottom here. Okay. And then let's just do one more. So just for example, I'm just trying to show that there's a distribution of these stresses inside our component. So it's not as simple as just looking at, you know, what's happening on the surface. We need to look at what's happening at the whole part. So here I have, oh, I'm not going to make those tensile. I'm just going to say, here's our thing. And our friend said torsion, right? So I'm going to have some T. All right. That one's going this way, so this one has to be going that way. T, well, what does that look like? Now I'm going to look down the center of my part. So what does it look like? Well, on one side, it's going to be trying to take the fibers up. And on one side, it's going to be trying to take the fibers down, right? That's what twisting is. We're trying to spin it, in this case, in a counterclockwise direction. And again, we have some distribution where on this case, it's max at the outside. So max here and min here. Okay, so great. What does that do for us? Why do we even care? Well, now let's go back to a real world scenario and talk about that. Okay, so here, this is something I talk about in my advanced biomaterials class, right? We would talk about machine design. A bolt is a machine in our component. So say I want to design a bolt to replace a fractured femoral head. So these are stainless steel bolts, sometimes chromium, sometimes titanium, but mechanical engineering heart. This is a lag screw. Basically, we can think about that. It just happens to be going in the body. Same technology you'd use to put a 2x4 in your basement against your concrete substrate, okay? So we have our fracture. We can obviously see this here. Well, as a mechanical engineer, what is my solution to most things? Well, step one, hit it with a bigger hammer. If that doesn't work, try to find an even bigger hammer and hit it again. So in this case, what do? Well, we hit it with 2 big lag screws and bolt those together. And that's what these are. So we have these lag screws going across our fracture site. And what happens in the hip, we have some kind of oblique load like this, right? This goes into your pelvis. This is the head of your femur. So this is maybe, let's just say you're standing on one leg. This is going to be body weight. All right. Well, now from what we were just talking about, realizing that there's stress distributions inside a component due to loading. This is a loaded component. It's a bum. Let's see what happens. So now if I'm going to look, say, here versus here where my screw is versus here, maybe below my screw, well, hopefully we can appreciate. Now let's see what do I have. If I take my body weight and I put that into discrete components, I'm probably going to have something pushing down on that way. As I have it drawn, I'm going to have something pushing on it this way. You know, I probably have, you know, some type of torsion this way because it's 3D space. So I have some type of torsion. And I may even have, you know, here, some type of moment. So I got a lot going on, right? There's multiple loadings going on. So how do I figure out what's going on at each of our ROIs or regions of interest? So I'm just going to call this ROI. Let's call this one 2, maybe this one ROI 1. As a mechanical engineer, if I'm going to design this screw and understand what's going on, I need to be able to tell what is happening there mechanically, right? And that's what machine design is all about, is understanding the different stress relationships in each of these. Why? Because I don't want that screw to fail when we put it in grandma or grandpa, right? If that fails, what's going to happen? Well, grandma or grandpa's going to fall down, break their hip. If they're over 70, the life expectancy of someone with a broken hip goes down drastically. So it's up to us as mechanical engineers to make sure this works. And it's not only the body. I like body stuff because I'm a biomed engineer, but this could be a bridge. This could be a component of a car, a component of an airplane, right? If it fails, the burden falls on us as mechanical engineers to ensure that doesn't happen, because people trust us, right? If you got in an elevator, for example, and you couldn't trust the mechanical engineer who designed it, think about how the world would fall apart, right? The public trusts us as mechanical engineers to know what we're doing. And that's what machine design is about, is looking at how we can design these components such that they don't fail. And that's critically important. So just going to use 1 minute. So let's just look at, say, ROI 2. I'm just going to draw a very generic shape here. See if I can get both on the page so we know what I'm talking about. Now I'm going to look at ROI 1. That's the interesting one where my screw is. So if I just take that, obviously this is a 2D representation, but what do I have? Well, I have stress due to compression on that face. I have stress due to compression on that face. Bending, so bending, let's see, if I was aligned maybe in this direction, I might have minus. So the bending force might be coming out this way. Stress due to bending. These are equal and opposite. So I'm just going to draw these here for completeness. And I may have some torsion on this component here. So this could be shear stress due to torsion, maybe plus shear stress due to transverse loading. So all of a sudden I have all these stresses on my component, and now I can compare those stresses. I can calculate those after you take machine design. I can compare those to my limit. So let's just say I look at a graph just real quickly in my last couple seconds here. So let's just say this is normal stress, shear stress. Don't expect you to know that, but every material I have, let's say titanium, has a boundary of those material properties. So let's just draw that boundary using a generic kind of plot like this. So this is, say, my material boundary for titanium. Okay. So what do I mean by that boundary? So if I go above those stress levels or that boundary, my part is going to fail. Okay. So that's the boundary given by any given material. Well, I go through, I do all the analysis on my region of interest. I determine where my stresses are, those being my normal stresses, my shear stresses, and I figure out my part is sitting right here. This is my ROI1. Well, what I can see is that, you know, I'm about, let's say about halfway to my boundary. So what that would mean is I have a safety factor of 2, okay? Well, this is a medical device. Is that good enough? Is that great? Should it be a safety factor of 5? Should it be a safety factor of 0.5? But now as a mechanical engineer, I can tell you how I can either finesse my material by changing the boundary. So maybe instead of pure titanium, I use a titanium alloy that increases the boundary or decreases the boundary. I make my screw bigger. I change the geometry, stress, force over area. If I change the area, I reduce the stresses. So now you've taken all these mechanical principles of understanding stress and been able to design a component. And this component can basically be used for a variety of things. I mean, anything in the world that you can think of. So let me just see if I had any other, So for me, the reason I show this, again, this is for my advanced biomaterials class, but it goes back to all the classes I teach, whether it's structural or not. I can look at this and use this analysis on polymers, on metals, on ceramics, on biological tissues. And why would I want to do that? Well, this is a picture here on the right. This is another orthopedic implant. It's a plate. And obviously this one was not designed great. If you can see down on the left, let me just circle it in red down here. Somebody messed up, those screws broke. That's a big problem, right? If screws break in the body, the plate's not working, thus we have issues. So as a mechanical engineer, I see this and it gives me heartburn, right? This was not designed correctly. So how do I go back? I redesign those. Look at the stresses, look at that in the computer space, look at that on the analytics space and all those things. And then lastly, you know, these are not simple analysis. We may be talking fundamentals here, but they actually build and build and build until you can look at very complex things. So for example, here I'm showing a schematic of an artificial knee. We have a metal component, we have a polymer component, we have a biologic and metal component, we have soft tissue components. And we need to know how to look at all of those under the boundary conditions and the loads we expect in the body. So that's, for me, what mechanical engineering is here at CSU, is combining all of that stuff and then bringing in, you know, what Dr. Roberts was talking about. So tolerancing, that is a huge part of everything I just mentioned. If the tolerances changes, these things don't fit in the body, the screws don't fit, they're not reliable, big issues. Comes back to what Dr. Bashara was talking about, that. Algorithms to actually solve for these stresses. By no means do you want to do this over and over and over again in your notebook. Can we develop algorithms that can look at these components, solve for these stresses, and actually determine what's going on? So in my mind, that's the 30-minute view of mechanical engineering and how we apply it, you know, from the fundamentals all the way up to advanced research here at CSU. So does anyone have any questions? If not, you can always reach out to any of us via the links. I'll post my link here in a minute, but we're happy to talk. I think CSU is a great place to get your engineering degree. And, you know, I think we have some pretty high quality stuff going on here. So any questions? All right. Well, thanks everyone. Appreciate your time. Good luck on finding your best fit in your engineering career. I don't think you can go wrong as a mechanical engineer. It's a fun place to play. So much cool stuff going on. So best of luck. Take it easy.
Thank you.
Thanks. Bye.
Bye, everybody.